An unfortunate incident that remains the only way to describe Starship Flight 9. It was supposed to be one of the most anticipated milestones, the first full reveal of the payload bay to the world. But then, it didn't open. The payload wasn't deployed. What happened today? Let's join Space Now as we uncover the truth behind that sealed door. This wasn't just a technical malfunction. It exposed what may be a fundamental design flaw revealed at the most critical moment. Although the flight wasn't a total failure, it left behind a significant question mark. Remember the moment at T+15:03. The world held its breath as the onboard camera showed the interior of Starship's payload bay for the very first time, a view that had never been made public before. For the first time, the Pez-style deployment system designed like a candy dispenser was revealed. Even though the payloads were only mock-ups, the emotions were real. It was the most comprehensive look, yet the internal layout, structure, and configuration were all clearly shown. Previously, Flights 7 and 8 ended too early in their missions for any such footage to be captured. So when Flight 9 reached C9 reached the payload deployment phase, everyone expected the door to open smoothly, cleanly, just like in the 3D simulations. But then, nothing. Silence. Not a single payload was released, and soon after, SpaceX confirmed the payload door had failed to open. Why on the ground, every test had gone flawlessly. Engineers inspected the system, loaded the payloads, and operated the door. Everything worked smoothly. But in space at the moment it mattered most, the system failed. So the question stands, what caused such a seemingly simple mechanism to break down? One analysis on Platform X attracted particular attention. It came from an engineer who designs submarine hatches. It might sound unrelated, but in fact, it's highly relevant. He pointed out that both submarine and spacecraft doors deal with pressure, but in opposite directions. Submarines resist external pressure from water pushing inward. Spacecraft, on the other hand, must deal with internal pressure pushing outward in the vacuum of space. That's why submarine hatches are designed to open outward, while spacecraft doors typically open inward, using pressure to help seal the system. But here's the twist. Starship isn't like other spacecraft. Its payload bay isn't designed to be pressurized from the inside. Without internal pressure to brace the door, it became loose, relying entirely on the mechanical actuator system to hold it in place. And that's where the critical vulnerability lies. In the vacuum of space, with no external or internal pressure to provide stabilization, the door becomes prone to shifting, vibrating, or even jamming. What was supposed to be a system purely for movement control suddenly had to absorb the full burden of torsional stress and dynamic loads from the rocket itself. The result: system failure, exactly what we witnessed on Flight 9. But that's not the only issue. Another weak point is the structural reinforcement of the payload door. As early as Flight 3, experts pointed out that the door was supported by only a few thin stabilizing bars, which lacked the strength needed to withstand high-frequency vibrations. It may be sufficient for ground testing, but once in flight, the combination of thrust and rotational forces can cause the door to warp, putting the entire payload deployment system at risk. Now imagine this: a thin, unstable door being forced open. What would happen? It could scrape against the payload deployment mechanism, cause physical damage, or worse, completely disable the entire module. That's not just a technical glitch. That's a mission-threatening flaw. So, what do you think? If you were SpaceX's chief engineer, how would you solve this design failure? Share your thoughts below. Join the discussion right here on Space Now. And remember, this is only the beginning. SpaceX is learning from this failure to improve the next generation of flights. But the real question remains, will they stick with the current door configuration or go back to the drawing board and design an entirely new system, just as they did with Falcon 9's landing architecture? Because a failed door can compromise an entire mission. If the payload can't be deployed, the mission is by definition a failure. So how do we fix it? SpaceX will need more than just a stronger actuator. They need a reinforcement system that can truly hold the door stable across every phase of flight. From launch through orbit, all the way to deployment in a vacuum. But reinforcement alone isn't enough. The system must also be precisely controlled. It needs to be perfectly synchronized with the actuator operating with the precision of a Swiss watch. Achieving that level of reliability will require fully integrated solutions, lock synchronization, hinge alignment, and advanced electronic control systems to ensure every deployment executes with millisecond accuracy. What if this system were integrated with AI for automatic misalignment detection? This technology has already been tested in the submarine industry and is gradually being transferred to aerospace applications. However, the core issue lies in the design philosophy itself. If SpaceX cannot pressurize the payload bay, then every component from materials and hinges to sensors and opening mechanisms must be fully optimized for a vacuum environment. That might require switching to different materials such as lightweight but high-strength alloys, or even adopting an entirely new deployment approach like modular sliding doors or multiple smaller hatches instead of a single large one. The deeper analysis of pressure dynamics and structural stability reveals that this failure wasn't just a hardware mishap. It's a case study in the complexity of aerospace engineering. Consider this: a single misaligned joint could jam an entire door in space. And that alone could turn a multi-billion-dollar mission into a costly lesson. What's your take? Was Starship's payload door design flawed from the very beginning? Share your thoughts in the comments below, and join the discussion with us here at Space Now. And don't forget to like and subscribe to Space Now, so you never miss a critical update on SpaceX's journey to the stars. Because solving the payload door issue isn't just about patching a mechanical glitch, it's a defining factor in whether Starship can become the backbone of humanity's interplanetary ambitions. For now, the door must be fixed to accomplish the most basic objective: deploying test payloads. Flight 9 failed to do that, and SpaceX understands clearly, without demonstrating this core capability, there's no moving forward to more advanced mission configurations. Once this door problem is resolved, what comes next? It's getting Starship into true orbital flight and successfully deploying operational payloads for the first time. Whether that's Starlink satellites or third-party commercial payloads, this milestone will mark Starship's real entry into the global space arena. This is when confidence is built. This is when SpaceX must prove its technological maturity. Because success here won't just unlock revenue, it will open the door to new commercial partnerships and lay the foundation for a truly scalable orbital economy. And there's one more critical detail: the payload bay is also where in-space refueling systems will be housed and deployed. If SpaceX intends to refuel ship to ship for missions to the Moon or Mars, then the door mechanism must function flawlessly. Any failure could cripple the entire refueling operation. No fuel, no interplanetary journey. Here's a final question for you. If the payload bay is the heart of Starship, then is it healthy today, or is it in need of a complete replacement? Big missions demand big machines, and Starship, if it wants to reach the Moon or Mars, won't just be carrying astronauts. It will have to transport tons of equipment, cargo, and infrastructure. From rovers and habitat modules to delicate scientific instruments, everything must be deployed flawlessly the moment Starship touches down. And guess what stands between mission success and total failure? The payload bay door. If it jams, the entire mission could collapse. No rover, no base, nothing. That's why the moment the door opens successfully, isn't just a mechanical step. It's the confirmation that the mission has reached its most critical goal. Can you imagine it? Dozens of tons of equipment, over $300 million in investment, all waiting on a single door to open smoothly. And SpaceX isn't planning for 10 years from now. They're aiming for uncrewed missions to the Moon, and possibly even Mars as early as next year. There's no time to spare. The payload door issue cannot drag on into next year. If SpaceX wants to stay on schedule for supporting Artemis or demonstrating capabilities on the Red Planet, this door needs to be flawless, zero tolerance for error. In other words, fixing the payload door is no longer a patch. It's a mission-critical prerequisite for the long-term strategy of SpaceX. From commercial operations in low Earth orbit to building orbital refueling stations to launching a new era of interplanetary exploration, it all starts with a door that works exactly as designed. Are you following each step of Starship's development? Let us know what you think SpaceX should prioritize next. A completely new door structure or a different deployment system altogether. How they handle this issue in the coming months will directly shape the speed and success of the entire Starship program. Let's keep a close watch, because SpaceX's next move might not just impact their mission. It could become humanity's first real step onto another world. Meanwhile, back closer to Earth, NASA faced a different kind of challenge. The Psyche spacecraft launched in October last year to study a nickel-rich metal asteroid, unexpectedly experienced a serious malfunction this past April. Its electric propulsion system suddenly shut down. The cause pressure in Psyche's primary propellant feed line supplied with xenon unexpectedly dropped. As a result, the spacecraft's Hall effect thrusters were no longer receiving adequate fuel to operate. Facing the risk of losing control, NASA engineers quickly activated the backup propellant line to bring the propulsion system back online. What is a Hall effect thruster? It's a high-efficiency ion propulsion system commonly used in long-duration missions previously deployed on numerous military satellites and deep space probes. However, these thrusters are highly sensitive to pressure fluctuations and propellant flow rates. Psyche's issue serves as a powerful reminder, whether in low Earth orbit or deep space, even the smallest technical detail, a fuel valve or a payload door, can determine the fate of an entire mission. By the end of April, NASA confirmed that a valve in the primary fuel line had stopped functioning as designed. The malfunction blocked xenon flow to the engines, resulting in the loss of pressure and eventual system shutdown. After evaluating multiple solutions, NASA announced on May 28 that it would switch to the secondary fuel line. Initial tests showed the backup system was functioning reliably. NASA now expects to restart the thrusters by mid-June and will keep the secondary valve open at all times to prevent similar issues from recurring. Once the electric propulsion system is reactivated, Psyche will resume its journey toward the metal-rich asteroid Psyche. The mission will use a planned gravity assist from Mars in May 2026 to accelerate its trajectory. The spacecraft is scheduled to enter orbit around the asteroid in August 2029. Once there, its suite of scientific instruments, including imagers, spectrometers, and magnetometers, will map the surface, analyze its composition, and measure the asteroid's magnetic field. Scientists believe that Psyche may be the exposed core of an early planetesimal, offering a rare opportunity to study the fundamental building blocks of planetary formation in our solar system. Despite the recent setback, the Psyche mission remains on track. The decision to shift to the backup fuel line demonstrates the importance of redundancy and rigorous planning in deep space exploration. Though many challenges still lie ahead, NASA's swift response in identifying and addressing the issue has reinforced confidence in the mission's success. We'll continue monitoring the reactivation process and the spacecraft's remarkable 3.5-year journey to one of the solar system's most fascinating targets. Meanwhile, let's turn to another major update from China. On May 28, the country successfully launched its Tianwen-2 mission aboard a Long March 3B rocket. The mission aims to collect samples from the near-Earth asteroid 2016 HO3, also known as Kamo-Oalewa, using a lander equipped with sample-gathering tools and a hopping mobility system. After completing a return flyby of Earth in 2027, to deliver the collected material, Tianwen-2 will continue its journey to the comet 311P Pan-STARRS sometime in the mid-2030s. This is a main-belt comet, distinguished by its multiple dust tails, a rare phenomenon in astronomy. If successful, China would become the third nation in the world to complete an interplanetary sample return mission. Such an achievement would significantly expand the scope of China's planetary exploration roadmap from the success of Tianwen-1 on Mars to upcoming missions like Tianwen-3 Mars sample return and Tianwen-4, which targets Jupiter or Uranus. Meanwhile, in the United States, NASA's Mars sample return program is facing significant budget pressures resulting in delayed timelines. Additional proposed funding cuts from the White House could further complicate the mission's future. In response, Elon Musk has suggested that if NASA's plan stalls, SpaceX's Starship could take over the task of transporting Martian samples at a fraction of the cost, though Starship itself is still undergoing rigorous testing to prove its reliability. With Psyche working to restore its propulsion system, Tianwen-2 accelerating toward its asteroid target, and NASA and SpaceX vying for leadership in Mars, sample return the next decade promises to be both a fierce competition and a shared pursuit in the exploration of the solar system. This is a pivotal moment where technological capabilities, national strategy, and spacefaring vision intersect and shape the future of each space power's role in orbit and beyond. What you've just seen is not just a technical failure, it's a wake-up call to the complexity and risk involved in conquering space. SpaceX, NASA, and China are racing against time. Every technical decision made today could determine the trajectory of an entire generation of exploration. Let space now be your guide as we track, analyze, and make sense of each breakthrough and setback. Subscribe today, because knowledge is the weapon, and inspiration is the fuel for every great journey.